All right, so find your little sheet that says fission of uranium-235. We're going to kind of pick up there with just a few quick reminders about what's going on here. Remember from last time that this is a uranium-235 nucleus. And we wrote some equations to kind of describe what happens. A neutron strikes a uranium-235 nucleus. The uranium-235 becomes uranium-236, which is actually a nucleus that can undergo fission. So it can rip apart because that's just what it does. Instead of undergoing radioactive decay, it undergoes fission. That fission creates two new products, some neutrons, and a whole lot of energy, which we said was described by Einstein's equation, E equals mc squared. We also talked about the fact that if you were to take these things and take the total mass of a neutron plus a uranium-235 and add all that together, and then you took all of these things, the two new elements and the three neutrons that came out, we'll call that the after total mass. The total mass before would be greater than the total mass after, and you were told this by the woman who since September 1st has been saying the mass cannot change, the mass cannot change, the mass cannot change, and now she stands right here in front of you and says, oh, by the way, the mass changes. Some gets lost. That is the mass referenced in Einstein's equation. We'll put it in quotes. Lost mass is the M piece of Einstein's equation. But Einstein's idea was mass and energy are the same form of, or different forms of the same thing. So we're probably better off not to think of it as lost mass, but to think of it as converted mass. We simply converted it to a new form. Okay, maybe now we're not in violation of anything that we hold to be sacred. So last time we got all of the equations written here. And I've kind of underlined in pink all of the different things that we were supposed to find. So today we're going to focus on just this first one. We just had to pick one to focus on. So we're going to put our attention on this very first isotope, or this very first equation. So if we were to put that in context with our picture, this is my neutron plus my uranium-235. Perhaps this piece is a barium-141. This piece is a krypton-36. And here's the three neutrons that come out. We're going to focus our attention there. Now, at this point, you're going to need your Chromebooks because I'm going to introduce you to a new website. Our new resource is going to be this half-life of the elements site. It has more information than you could ever hope to need or want. You'll have to open it outside of Schoology. It's far too complicated to run within Schoology. And so here we have arrived at the half-life of the elements site. Here we have a periodic table. You will notice that they have put the inner transition metals back in the periodic table where they belong. Since we're talking about fissioning uranium, let's go to uranium's page. So find the U down there in the periodic table, click on it, and it will take you to a page that's got all sorts of information about uranium. Okay, so here's the stuff that's on the periodic table. But the part I'm really interested in is down here. Here are all the known isotopes of uranium. Stable isotopes, there are none. All uranium is radioactive. These are your naturally occurring isotopes of uranium. The Earth naturally has uranium-238, uranium-235, and a tiny amount of uranium-234, but we even kind of know where that comes from. It was the end of step 3 in our decay chain for the uranium-238. Some uranium-234 came into existence, but then it kind of moved on and became other things, which is why there's not a whole lot of it. From here, we can pick uranium-235, since that's the one we want to talk about today, and we can click on that, which takes us here to information specific to uranium-235. So here it is. It tells you its half-life, which we'll learn about later on today. It tells you how many protons, how many neutrons, and a lot of other things too. If you want to know what kind of decay it's likely to undergo, you can click on decay, show decay modes. There's a 100% probability that it's going to undergo alpha decay. If you want to know what it becomes lead-207 when it becomes stable. So you get all that information from there. The information that we want today is a very specific mass on uranium-235, because we're about to try to take the total mass of this and the total mass of this and make a comparison. But we need to know not uranium's average mass, but actually what uranium-235 is going to weigh. And that's what we're seeking today from the half-life of the elements. So if we look on here, the atomic weight for uranium-235 is this right here. And I want you to snag it out to 6 decimal points. Okay, so take 6 decimal places off of that. So we've got 235.0433930 AMU. And then you're going to calculate the total mass of the reactants by taking the mass of a neutron, which I've given to you, adding it to the mass of uranium-235, and putting in there. I'm going to highly recommend today that everybody use their own calculator and confirm with your partner, because it is so easy to miscue on this. And from here, you're just going to go forward. Once you've got that, you're going to look up the mass of the barium-141, the mass of the other piece, which we now know to be krypton-92. Here's 3 neutrons. Add that up. And according to what we have talked about, this number, total mass of reactants, should be smaller than this number, total mass of products. And then you're going to go forward and finish up the rest of this sheet. So working with your team, work your way through this, and let's figure out how much energy is actually given off by the fission of uranium-235.